Example: solve the problem by dual simplex method. Minimum z equals to 2x1 plus x2 subject to 3x1 plus x2 greater than equal to 3, 4x1 plus 3x2 greater than equal to 6, x1 plus 2x2 greater than equal to 3, and x1 and x2 greater than equal to 0. Solution. Step 1. First we write the problem in the following form: maximum z dash equals to minus 2x1 minus x2, z dash equal to minus z, subject to minus 3x1 minus x2 less than equal to minus 3, minus 4x1 minus 3x2 less than equal to minus 6, minus x1 minus 2x2 less than equal to minus 3, x1 x2 greater than equal to 0. Step 2. Adding the slack variable x3, x4, x5 in each constraint, we get minus 3x1 minus x2 plus x3 equals to minus 3, minus 4x1 minus 3x2 plus x4 equals to minus 6, minus x1 minus 2x2 plus x5 equal to minus 3. Consequently, in the matrix form, the constraint equations can be written as matrix minus 3, 1, 1, 0, 0, minus 4, minus 3, 0, 1, 0, minus 1, 2, 0, 0, 1 into column matrix x1, x2, x3, x4, x5 equals to column matrix minus 3, minus 6 and minus 3. Step 3. Constructing the starting simplex table. Table 1. Cj minus 2 minus 1 0 0 0. Basic variables cb, xb, x1, x2, x3 beta 1, x4 beta 2 and x5 beta 3, x3, x4, x5 0 0 0, xb minus 3 6 and minus 3, x1 from here minus 3 minus 1 0 1 0 0, and similarly minus 4 minus 3 1 0 1 0, and a third row minus 1 minus 2 0 0 1. So z dash equals to cb into xb equals to 0, and delta j is 2 1 0 0 0. Here x2 will enter and x4 will come out, because step 4. To find the leaving vector beta r, since xbr equals to minimum of bi, xbi and xbi is less than 0, so equals to xb1, xb2 and xb3, minimum of xb1, xb2 and xb3 equals to minimum of minus 3, minus 6 and minus 3 equals to minus 6 equals to xb2. Here r is 2, so we must remove beta 2 from the basic matrix. Step 5. To find the entering vector for the predetermined value of r equals to 2, delta k upon x2 2, maximum delta 1 upon x2 1 and delta 2 upon x2 2 for x2 1 is less than 0 and x2 2 is less than 0, so equals to maximum of 2 upon minus 4 and minus 1 upon minus 3 equals to minus 1 upon 3 equals to delta 2 upon x2 2, hence k equals to 2, so we must enter the vector a2. Step 6. In the table 1, the key element is minus 3, so we get the following transformation table. In in the usual manner in table 1. In place of 3 we will make unity, and the rest of the entries of the column we will make 0 0, and so after making this we will get the table 2 as cj -2 -1 0 0, basic variables cb xb x1 x2 beta 2 x3 beta 1 x4 and x5 beta 3 x3 x2 and x5, because x2 will enter in place of x4. So here we will make 1 and rest entry 0 0, so 0 -1 0 -1 -2 -1. So here after making 1, so and rest of the entries will 4/3 1 0 -1/3 and 0, and here after making 0 the entries are -5/3 1 1 -1/3 and 0, and also here I'm making a 0, so entries will be 5/3 0 0 and -2/3 and 1. So z dash cb into xb equals to -2, and so z equals to 2. So 2/3 delta j 2/3 0 0 1/3 and 0. x1 will enter and x3 will come out, because delta 1 equals to cb into x1 minus c1 equals to 2/3, and delta 4 cb into x4 minus c4 equals to 1/3. Step 7, to find the leaving vector beta r, since xbr equals to minimum of xb and xbi is less than 0, so equals to minimum of xb1 equals to xb1, xb2 and xb3 both are positive, hence ignored, therefore r1, so we must remove the vector beta 1. Step 4, to find the entering vector ak for the predetermined value of r equals to 1, since delta k upon x1 k equals to maximum of delta 1 upon x1 1 and delta 4 upon x1 4 for x1 1 is less than 0 and x1 4 is less than 0, so equals to maximum of 2/3 minus 5/3 and 1/3 upon minus 1/3 equals to minus 2/5 equals to delta 1 upon x1 1. So k equals to 1, so we must enter the vector a1. To finding the transformation table, in the table 2 the key element is minus 5/3. This is the key element 5/3, and x1 will enter and x3 will come out. Here in place of 5/3 we will make 1, and the rest of the entries of this column will make 0 0. After the making we have the table 3, basic variables cb xb x1 x2 x3 x4 x5. x1 will enter, x2 x5 and minus 2. Here we will make unity, so here we get 3/5 1 0 minus 3/5 1/5 0. Here we will make the unity 0, and so we will get entries 6/5 0 1 4/5 minus 3/5 0, and here also make 0, so entries will be equal to 0 0 0 1 minus 1 1. Z dash equals to cb into xb minus 12/5, so z equals to 12/5, delta j equal to 0 0 2/5 1/5 and 0. Now we get transform table 3, delta 3 equals to cb into xb minus xb cb equals to 2/5, and delta 4 equals to cb into x4 minus c4 equals to 1/5. Since the basic solution of x1 3/5 and x2 equals to 6/5 and x3 equals to x4 equals to x5 equals to 0 is feasible in this stage. So this is the required optimal solution, giving z equals to 12/5.